So let's do our first example for one-way Anova. A regional manager wants to know if there's a difference between the mean amount of times that customers wait in a line at a drive-through for 3 of her stores in the region. She samples the wait times at each store. Use an Anova test to determine if there's a difference between the mean wait times for the 3 stores at the 0.5 level of significance. Okay, so think about what we're trying to do. She's got 3 distinct stores, and she takes the wait times because she wants to see if there's any difference in the wait times for store 1, 2, or 3. And they do this a lot in retail, any kind of thing like that, especially with like Amazon, Target, those kind of things, to see if there's differences in the wait times among the stores, packages getting delivery, any kind of thing like that. And this is a good way to compare, again, means to see what the differences are. So here's what the data looks like. And I'm going to call this summarized data because I have it as store 1. I have all the data for store 1 going down, store 2, and store 3. Now, my hypotheses for example 1 are that the null is that the mean of store 1 equals the mean of store 2 equals the mean of store 3. And of course, the means aren't going to be exactly the same, but they're going to be close. And that's what we're looking for, is to see if there's really any significant difference in the mean wait times. And of course, we do that with means. And with the null hypothesis, remember, you have to have the equal sign. And as you can see, I have 2 equal signs up there in the null because I want to know that the mean of store 1 equals the mean of store 2 equals the mean of store 3. And remember, when we're doing that, we're comparing all the means together. So I'm also saying that the mean of store 1 equals the mean of store 3. My alternative is that not all the means are equal. It could be that 1 is different. It could be that 2 are different. It could be that they're all 3 different from each other. Again, I can't tell in this test where the differences is. I can make a guess, but there's other tests that we make as you go into a deeper look at statistics that shows you the difference. So now I'm going to use Minitab to solve the problem. Okay, I'm going to open Minitab, and here I've already copied and pasted my data in there. So what I'm going to do is I'm going to go to Stats, Anova, one way. So I want to change this to where it says that there's separate, that each data is in a separate column for each factor level. Factor level in this case is just a different word for sample because I have 3 samples, right? 1 from store 1, 1 from store 2, and 1 from store 3. That's how I think about it. So I click in the box and it brings me up everything that's in my columns to this big box to the left. I hear store 1, click on store 2, click on store 3. Options, remember, at a 5% level of significance, so the 95% is good. I will check assume equal variances, and the type of confidence interval is 2-sided. I hit OK, and I hit OK, and it's going to give me a lot of information. So let's go look what it did. First thing it gave me was my hypotheses with my significance level. It's a good way to check yourself to make sure you're correct. Factor levels, it said that I used the 3 factors, store 1, store 2, store 3. Always check yourself because as you start getting more and more factors in there, it might be easy to overlook one. Now here's the analysis of variance table that we talked about before in the beginning of the PowerPoint. It gives it to you really nice. You have your different degrees of freedom. You have your F value and you have your P value. The F value is 2.29 and the P value is 0.129. And if I keep going down to model summary, I have it where I have the R squared. We haven't really talked about R squared yet, but it helps us to account for where the data is coming from. We're going to talk about it more in regression, but just know an analysis of variance can give you an R squared. The next thing it gives me is it gives me store 1, store 2, store 3. It gives me each of their sample sizes. It gives me their sample means, sample standard deviations, and their 95% confidence interval. So one thing we're doing with these means is we want to see if they're pretty similar. And most of the time, if you can look at the means and kind of see it based on the confidence intervals. Another way is Minitab makes you a graph. So you can see here, here's the mean of store 1, mean of store 2, and mean of store 3. So we're kind of looking, store 3 is a lot lower than it looks like than store 1 or 2. But remember, we're looking at the averages. And here we can see the overlap of the confidence intervals. This one's a little bit higher, this one's a little bit lower. But again, the true way for us to do that is to look at the p-value. But let's look at another thing that could happen. What happens if my data is, I'm going to push my data up here. What if my data is like this? Okay, I have the data here. It's all in one column. And I'll show you what I'm going to do. So say this is my times, and this is my stores. Okay, and say this is 1, and this is 3. And you don't have to do this. I'm just giving you an example of what the data could be. And then those are the 2s. Okay. Usually you're going to see this data if I give you an Excel file, your project data, even maybe on the final exam, or anytime in real life. You're going to get the data. It's not always going to be in this pretty summarized. It's going to usually be, I call this kind of raw data, where I have all the times and then I have the stores. So you can see like 2.34 goes to store 1, down here 2.45 goes to store 3. So again, it's a different way of looking at the data set that's over here. We handle it pretty much the same. We go to Stat, Anova, one-way Anova. So I'm going to click on response data in one category in one column for all the factors. I click on it. The responses are the times and the factors are the categories. Again, I go to options and then I hit OK. And I'm given, if I go look again, I'm going to make this a little bit lower. I'm giving the exact same thing. Nothing changed. It's all the same. And it should be because the data is all the same. But again, your data can be in 2 distinct different ways. So now that we've seen that I've concluded both ways, let's go ahead and make the formal conclusion. So if I go back to the PowerPoint and if I scroll down, and again, in the PowerPoint, I have the ways to solve this. I have it for the raw data and the summarized data, as I called it. Okay, just because they're the same thing. It's just how you lay out the data. I made it summarized in raw just to help with it. Okay, so let's get the results. So again, the F value was 2.29. The P value was 0.129. Store 1 has a sample size of 7 and a mean of 2.170 wait time and a standard deviation of 0.557. Store 2 has a sample size of 7 with a mean wait time of 2.416 and a standard deviation of 0.603. And Store 3 has a sample size of 7 with a mean of 1.823 and a standard deviation of 0.372. All right, let's conclude it. So remember, I've got that 0.05 level of significance. Since 0.129 is greater than 0.050, I fail to reject the null, which means my null is true. So the mean times are the same. And I even went back here and put your original null hypothesis. So at the 0.5 level of significance, there is no difference between the mean amount of time that customers wait in line at the drive-through window for the 4 stores in her region. Okay, and remember, she had asked up here, if I go back to the original hypothesis, she wanted to know if there was a difference. And I concluded with the difference. But it's not even that hard because think about it. When I look at my hypotheses, there's really only 2 ways I can conclude it. That they're the same or that they're not the same. So because she asked for the differences, I just conclude, and I'll go back here again, that there are no differences.